may measure 10 meg reverse bias. Okay, understand that. But what they've done for us, uh, is the meter, instead of displaying the ohms, it displays the volts required to make a certain current flow, right? You understand? So when you flip your meter to ohms, it becomes a power source, right? Y'all understand that? So if it's a power source, and if it says, okay, I'm going to put out whatever voltage is required to cause 1 milliamp flow. So the meter automatically raises its voltage until 1 milliamp flows, and then it displays, and now the math is easy, right? 1 milliamp, 1 volt, right? You understand? R is equal to V over I. That'd be 1 over 1 milliamp, and your meter would show 1K. Right? You understand? So what we do when we put it on the diode scale is it displays the voltage. Instead of doing the math, it displays the actual voltage the motor had to put out to cause the thing to work. So that means if we put it on the diode scale, it is still considered an ohm meter, right? You understand? Even though it's not displaying ohms, now it's displaying volts. That was required to cause the conductor, the thing to conduct. That makes sense? If we want to check it out, but you can use the ohm scale if you want to. It's just that it's not going to show 0.7 and it's not going to show overload, right? You understand? It's going to show you maybe 1K if you forward bias, and it's going to show you like 10 meg when you reverse bias. Y'all understand? So yeah, you can use your ohm meter. But still, that does not tell me if it's a germanium junction or whether it's if it's an LED. An LED, it's heavily doped. I mean, it has a breakover voltage. It starts conducting around 2 volts. So that means I can't tell what it is, right? If I use that diode scale, then what it'll do is I can tell if it's silicon, I can tell if it's germanium, or I can tell if it's a diode. And it's really neat. We'll look at this. We'll see if your meter can do it. Most of your multimeters now will actually put out over 2 volts, and it'll turn an LED on. So you can put it on diode scale and forward bias it, and the LED will come on. But it's going to measure over a volt, right? You understand? Because of the way it's doped. And then, of course, when you hook it up backwards, the LED will turn off, and it should show you overload. So a light emitting diode that's an LED. It's a light emitting diode. So if you forward bias it, it does what? Turns on. If you reverse bias it, it turns off. But if you put 5 volts on it, you're going to have to protect it with the resistor. So once you turn it on, anything above that is considered a short circuit, right? You understand that? So this is why just about all the time you'll see an LED in series with a resistor. But it's not designed to rectify because it drops over 2 volts, right? You understand? It's strictly a display device. So this is what we call the characteristic curve of a diode. This is used in what we call third approximation, which we don't use that much. So this is actually what happens. As soon as you forward bias a diode, there's going to be a small current flow through it, even though it hadn't exceeded the barrier voltage. But as soon as you exceed the barrier voltage, then what's going to happen? It's going to start conducting, and we call this the knee. So we always want to operate it above the knee, right? You see why they call it the knee, right? And then it has a slight slant as it goes up because there's still an R inside the diode even though it's forward biased. But here it's going to be, once it does it, it's going to be linear. You could actually calculate the resistance of the diode when it's forward biased. But normally they'll give you the resistance of the diode. Now we don't usually worry about this because notice there's such a slight slant. Sorry about marking. In fact, I don't know. They called it a dry rate board. That's on the rate that has to leave it up there. Now, when we reverse bias it, then this is going to go a long way over here, right? You understand? That's why they got these little dashed lines right there. And then you hit what we call the reverse breakover voltage. In a regular diode, so this guy here is dropping all these voltage, and now you're putting a lot of current through it. P is equal to V times I, right? You understand? So all of a sudden the diode just does what? It burns up. So if you exceed the breakover voltage on a regular diode and you don't protect it, then it's going to cause problems. Now this is for rectifier diodes and small signal diodes. We do have a diode that's designed to operate over here. We call it a Zener. We'll look at that. But this reverse voltage right here stays fairly constant. Can y'all see that? Which is pretty cool. It changes a little bit because of the R of the diode, right? You understand? But your reverse R is going to be a lot higher than your what? Than your forward R, right? Does that make sense? So regular diodes, we never, ever, 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 ever want to make it do this. We call it the reverse breakover. Now we're going to do it on purpose, but we're going to protect it with like a 10 mega ohm resistor. So we're going to see it break over. We'll do this as in a class because we're going to do the one in 914, and it's got a breakover voltage of around 50 volts. But we're going to to make it break over, we're going to have to put almost 90 volts on that. So we'll do this as a class, and I'll do that, right? Because that's pretty high voltage. But we'll deliberately break it over. But what we're going to do is we're going to put a 10 mega ohm resistor in series with it. And then we'll measure the current flow. So we'll look at the 10, we'll originally look at it, and the 10 mega ohm is going to actually drop almost no voltage at all because the diode is reverse biased, right? You understand? And then all of a sudden the current is going to do what? The voltage drop across the 10 meg is going to shoot up as soon as it hits the breakover. So we'll break one over. It's actually, I think, the first lab that y'all will do. And then, are we okay? So there's a characteristic curve. We call this what? Breakover. And this is, where do we find this information at? We find it in the data sheet for the diode. You look up the part number, right? You understand. And then it'll come up and it'll tell you the VF of the diode. What's VF? That's the forward voltage drop. This is called VF. Now it gives you two measurements. It gives you a typical, and then it usually gives you a maximum. Now what we do is we don't. This would be, if I was going to do this, an engineer might be really interested in this, but once we're not interested in that. But what we're going to do is we're going to use what we call this is the diode symbol, right? So if this right here was, this is going to be on the test, and somebody in this class is going to miss it. If this was silicon, what should we expect it to drop? Around 0.7. It's not going to be 0.7. It's going to be around that, right? So we use what we call second approximation, which means we consider this guy to be 0, and then when it hits 0.7 of a volt, we consider it to be there. Because we don't know what it actually is, but it's close enough so I'll know what to expect, right? And we're used to this because we know that a resistor, when we do our calculations on our resistor, if this is a 10K, we use 10K, but what's the odds of it being 10K? Very low. Because that's why we add tolerances, right? You understand? So 5%. So, but when we do the math is perfect, right? You understand? But when we make our measurements, almost never will your measurements be exactly what you calculated, but they'll be what? They'll close enough to tell if it's what, if it's good or it's bad. So just because I use second approximation, that might not be, it might not drop exactly 0.7 of a volt, but it's going to be what? It's going to be close enough for our math. So we either know it's what? It's good or it's bad. So if I'm expecting 7 volts and I measure 6.5, then that's great, right? You understand? Or if I measure 7.8, that's still great. If I'm expecting 6 volts and I measure 10 volts, then what? Yeah, you know something's definitely wrong. So we use what we call second approximation. First approximation is you consider the diode to be ideal. As soon as you forward bias, it cuts on. As soon as you reverse bias, it cuts off. And we use that, anything usually when we're operating above 50 volts, we go ahead and use the first approximation. If we operate below that, we usually use second approximation. So all our circuits, we use second approximation. So if this is 10 volts, what would be the voltage using second approximation? Is the diode forward or reverse bias? Yeah, the cathode is pointing toward the negative and the anode is pointing toward the positive, right? You understand that? So how much would the resistor drop if this was silicone? Around 9.3 volts. Everybody okay? Because of Kirchhoff's law. Kirchhoff's law says the sums of the voltage drops. Now, what if this right here was silicone? What would the resistor drop if this was 10 volts? Well, let's look at the diode, and this is the mistake everybody makes. What you got to do is you got to picture that diode as a closed switch when it's a forward bias, and you got to picture it as an open switch when it's reverse bias. So if I measure across that resistor right now, it's going to measure pretty close to 0 volts. Our meter will measure 0 volts. And if I measure across the diode, it's going to measure 10 volts. Because it's reverse bias. It's acting like I guarantee you somebody in this class, I'm going to throw a diode up there, I'm going to say silicone, and you're going to say 0.7 of a volt, 9.3. And it's going to drop all of it because it's what? It's reverse bias, right?
So reverse bias, it acts as an open switch.
Yeah, right now, if I was to go over here on these light switches right here, and I was to measure the voltage across those switches, what would I measure? What would we measure? We measure 0 volts because they're all closed. They have no resistance, right? You understand? If I go over here and open that light switch, this light right here turns on, what would I measure across the switch? I'd measure 120 volts, right? You understand? And that's what gets people messed up. They think things have to drop voltage, and it don't. When we reverse bias it, the leakage current is so small. I mean, we're talking about the nanoamps, right? So if this was a 10K ohm resistor, and I put a nanoamp through a 10K, it's going to drop what it would drop because the leakage current is so small. And we're going to see the leakage current. So what we're going to do is we're going to take a diode, and we're going to put it in series with a 10 mega ohm resistor. And we're going to bring it up until it breaks over, and then I'm going to bring a soldering iron up to it, and we'll see the current, we'll see the voltage drop across the 10 meg go up because the leakage current is going up, right? You understand that? We'll see that. Like I said, we'll do that one as a class. But I can almost guarantee somebody in this class, we got 7 people in the class. When I put this on the test, somebody's going to say 9.3. Which one of y'all is going to do that? Huh? Yeah, it'll be that one. And all I have to do is say silicon. If I say germanium, you'd say, well, it's 0.3 of a volt, right? You understand? But you don't look and see if the diode is what? Forward biased or reverse biased, and that's the problem. People don't look to see if the diode. So if the cathode is pointing toward the positive and the anode is pointing toward the negative, then the diode acts like an open switch. And by George, it acts like an open switch because, like I said, the leakage current through there is so small that our meters can't measure unless we do something crazy. These things come in all types of packages. So they come in packages like this. We'll look at later on where we have a special circuit we hook up, where we have two of them, like this. And then this side right here is connected together. Well, you can get these, they'll be in a 3-pin pack like that, which looks like a transistor, but it's not. It's just a set of diodes that's hooked like this. So these guys come in all types of packages, right? But they usually identify the cathode. Normally they don't identify the anode, they identify the cathode. And I think I showed y'all that. On small ones, we use the watt. We use the little watt. We use that little band to identify the cathode. Might be silver, might be black. It depends on the diode. I think I passed around the 1N914, and it uses a black band because the package is glass, right? You understand? And then I passed around the 1N the 4000s, and it was black. It was plastic, so they used a silver band. But they're going to do that. The bigger the diode, though, the more likelihood. The bigger the diode, what they'll do is they'll start doing what? They'll start putting a little symbol of the diode on the device itself. So don't assume, but if they don't put the symbol, you can figure out the anode and the cathode with your own meter, right? Everybody okay? Set to the diode scale. Everybody okay? We've already talked about this, first approximation. So first approximations, we think it's like this. No VF, right? No current flow, no leakage current. That's around what voltage? 50 volts. Because what's the difference between calculating, 40.3 and 50? It's just not enough to even worry about, right? You understand? So this is first approximation. We're going to use what we call second approximation, which we're going to come over here and say the diode, when it's forward bias, it's going to drop about what for silicon? 7/10, and hopefully we never break it over. And this is going to be close enough, right? You understand this, and it makes it a lot easier. And then, of course, third approximation is where you actually deal with the actual true curves and the resistance of the diode and all that other kind of stuff. Engineers might play around with this, but we don't fool around with this at all. Okay? So in this class, what are we going to use? Second approximation. Everybody okay? Because everything we're going to deal with is low voltage, except when we deliberately break it over. Everybody okay on testing about a diode? Using a multimeter is the easy way. If we have it on the true resistance scale where it translates the voltage into R. So technically, a meter cannot measure R directly. It does it indirectly, right? You understand that. How does it do that? How do these meters do it? It outputs a constant current, right? You understand. And then what does it do? Then it calculates V over I. And it's usually, if it's 1 milliamp, it's just a point. It's just doing what? Just putting a decimal point somewhere, right? You understand that. But if we do it on the R scale, what should we? We tell our meter to convert it over to resistance, and we should expect a real high resistance when we do what? Reverse bias it, and we should expect a lower resistance when we do what? And it's going to be a big ratio between the two. Let's see if this meter will do that. So let me find the diode. I didn't put up my. So this is a 1N4001. And we looked at the data sheets on that, right? And this one has a breakover voltage, I think around 50 volts. I don't really like this. Let me put it on ohms. We're going to have to redo this. People, I like a meter. I personally like a meter that is a manual ranging meter, which is what this meter is. There we go. So guys, you got to be real careful when you put your meter on an extremely high scale. So I've got it on the 40 meg scale, and this is why. What's it? Who's it measuring? He hasn't measured. So if I was to come over here and grab this thing like this and do this, then I'm in parallel with that, right? Understand? Everybody okay? So what you need to do in this situation is you can hold on to one side, that's fine. But what you need to do is come over here with the other side and try to put it up against something and do it like this. So this meter won't measure it. So this is reverse bias. And then this right here is forward bias. So this is showing me meg, but the other way it was showing me what? Overload. Now, some of your newer meters will measure reverse bias. It won't give you an overload. Everybody okay? Now, this is R, of course, but I don't know whether it's germanium. I don't know if it's silicon. I don't know if it's an LED. Of course, an LED is usually pretty straightforward. But if I put it on this, this is the maximum this meter will put out. So it puts out about 3 volts. See, because this is, I've opened, right? So I can come over here now and put it, now you can do this. And this is, I know this is silicon, right? That's forward bias. And I'll flip it over here. It's going to show me this on this meter. I don't like this meter. Because what it's doing is it's not translating this as an overload. It's actually showing me the voltage. So this is the only thing I don't like about this varimeter. See, it's showing me the same thing. It's showing me the same thing. Now this is an open, right? You understand? And it's showing me the 300 millivolt. So, but all your newer meters will come up and show you overload if you reverse bias it, and show you the VF if you forward bias. Everybody okay? So if I measure a voltage in both directions, then it's either not, it might not be a diode, guys. But if it is a diode, that should be what? Bad. If I measure 0 forward bias, that means it's shorted. It'll usually measure 0 in both directions, though. Are you okay? So diode P-in junctions are really neat. So any device that has a P-in junction, we can check it using this technique. So we have devices called bipolar junction transistors, which use P-in junctions. So we'll be able to check that with our meter. Are we okay? So this is kind of like my meter. We're showing 2.6 volts when it's reverse bias because that's the maximum the meter will put out, right? Does that make sense? I mean, they've changed that over our new meter. If you check a diode in circuit and it checks good, then this thing is good. If you check it in circuit and it checks bad, then we need to isolate it by pulling up one of the leads. Everybody understand why? It's almost impossible to check this because how much resistance does a transformer have? Well, let's just, how much, is it low or is it high? So what would you expect the resistance of a transformer to be? Would it be a low resistance or would it be a high resistance? Why? It's nothing but wire. Y'all understand that? It's nothing but wire. It gets its opposition from something called X sub L. X sub L. Yeah, inductive reactance. It's not it's inductive reactance. So this is the opposition right here, and can you see what it does right here? It varies with what? F equals what? And then this is the value of the inductance. We call this inductance. So as soon as I put AC on this thing, there's an opposition, right? But it's not resistance. It's what we call inductive reactance. But if I measure this with an ohm meter, on the secondary side, it might be like 10 ohms. And then the problem is when I check my diodes, if I leave my transformer hooked up, I'm gonna measure 10 ohms in both ways, right? You understand? So that means that's when you definitely got to isolate your diode, especially when you're using it in a power supply, which is what this is, which we hadn't talked about yet. So most power supply consists of the same basic units. They usually consist of a transformer. What does a transformer do for us? Yeah, so this is what we're actually going to choose a transformer that's going to give us what we want over here, the output of the power supply. So that depends on the size of the transformer, whether you want to step it up or step it down. And then we're going to have a group of diodes, which we're fixing to get into. And this is going to be our rectifier. So what does the rectifier circuit do for us? Converts AC into pulsating DC. And we'll look at that in a minute. This right here is going to be the filter. The filter converts pulsating DC into what we call unregulated DC. And then we'll have some type of regulator. What do y'all think the regulator is going to do? That's going to regulate the voltage. So this is the basic makeup that we're working on. So what we're doing, we're going to look at the transformer a little bit. Right now we're going to look at, then we're going to get into the different types of power supplies we can have. Then we're going to filter them, and then we'll play around with that. That's a capacitive filter. One of the main purposes of these active devices are these devices like capacitors are filtered. Capacitors work out real good, right? We could come over here and put an inductor in series, and it would do the same thing. But the problem is inductors cost a lot of money. So they're more expensive than capacitors. So the predominant filter is capacitors. Even in your switching power supplies, you probably end up with both of them because they save money on the actual components themselves.
What is the filter?
Huh? The filter. So we start off with you mean the function in the power supply? A filter in electronics is a device where we can manipulate frequency. So, and y'all should have touched some of this in AC. Some of y'all had. We have what we call high pass filters, low pass filters, band pass filters, band stop filters. So what we're doing here is we're basically getting rid of the high frequency component compared to DC. Now you're saying, well, 60 cycles is not high frequency, but it's high frequency relative to 0 hertz, right? You understand? So that's what we're going to do here. So this would be what we call a low pass filter, but the low pass is going to be almost 0 hertz. Are you okay? So filtering is what we do, and basically capacitors and inductors, that's our main function in life, is to filter, to get rid of frequencies that we want, that we don't want. Now we do it, most of the time we do it electronically, now. We use a thing called a phase-lock loop circuit. But originally, this is the way we tuned our radios, our TV stations. We set up a tuned circuit, right, or a filter circuit. We'll come back to this because this is a little harder. This is the type of rectifier we call a bridge rectifier. Different circuits have different names. And then we'll come back to troubleshooting. So what we're going to do now is actually get into our power supplies, guys. DC. And when we use the term power supply, usually we're referring to a circuit that converts AC into DC. So what advantage does AC have over DC? Yeah, hard to store AC. Almost, it's real hard to store AC. The biggest advantage of AC, besides for motors, guys, is I have a conductor, and I'm trying to get power. How many of y'all live next to a power station, power plant? Where's the power plant at? You get your power from? We get our power from the Tennessee Valley, from up there, North Alabama. This Bessemer's gets their power from TVA. How in the world do they get that power down here? Well, they got to get it through conductors. Now, what's wrong with the conductor is all conductors have an R. And V is equal to I times R. So if I put a current through that thing, that wire is going to, and we think about wires this big, right? But think about the wires that Alabama Power is trying to send this thing through. It's miles, right? You understand? So they're trying to send it through a wire. So if that sucker think about your car. Your car, when you start your car, your starter probably pulls about 50 amps. If that wire had 1 ohm of resistance in that wire, even though it's that short, it would try to drop 50 volts, right? You understand? And your car wouldn't start, right? You understand? Think about this, the wires that Alabama Power is using. We're talking about miles, right? You understand? And they're trying to send power through those wires. Well, if it had 1 ohm of resistance per 1,000 feet, right? You understand? And I'm going 50,000 feet, then that's going to be 50,000 ohms worth of resistance. If I try to put 1 amp through that resistance, right? You understand? It would do what? It would drop 50,000 volts, right? You understand? Everybody okay? So what they're trying to do is they're trying to get power, not voltage, not current. They're trying to get power to your house, right? You understand? So technically, if everything in the system was 100% efficient, if you turned on a 100-watt light bulb at your house, how much power would Alabama Power give you? 100 watts. So they're not concerned with transmitting voltage. They're not, and voltage don't move anyway. What they're trying to do is lower that dang current, right? You understand? So what? So those wires don't drop a lot of voltage. So the magic formula for power is P is equal to V times I. Well, if I rearrange that, I can say I is equal to P over V. So if I'm trying to send you power, the higher I can send that voltage, what happens to current? Current goes down. Y'all understand that? Now, the problem we have is how to step voltage up and step voltage down. Now, originally, when Edison set up the first power grid, he used DC. Now, how can you step DC up and step DC down? You can't. Easily. We can do it electronically, right? You understand? But we can't do it with DC itself. So they had to put a power plant about every mile just to support sending that power over the wire, right? I don't know what they used, but they didn't step it up and they didn't step it down, right? Y'all understand that? So they said, okay, what can we do? Well, Tesla invented AC. So DC was discovered. AC was invented. So AC doesn't necessarily, they found out electric eels, by the way, can output AC. Huh? Electric eel. They figured it out. Electric eel can put out, I think, so many volts AC to stun things. If they want to stun them, then they can put out a lot of DC to kill if they want to. But they didn't know that then, right? You understand? So AC we can generate, and we generate it magnetically. But to induce a voltage into a wire, we need three things. We need a magnetic field. And then we need a conductor. And then we need what we call relative motion. So that means if I've got a piece of wire, and if y'all have ever been in the motor control labs, we do this over there. We got a big magnet, and we got a spool of wire, and we just move it across the magnet, and you'll see my meter deflect. I can leave that wire stationary, and I can sit there all day, and my meter never moves because I've got everything. I've got a magnetic field, I've got a conductor, but I don't have what? I don't have motion. Everybody okay? This makes sense. So this is the way our alternators work. Now, but AC gives me everything. So AC generates a magnetic field, right? Then I can have a bunch of conductor loops, but AC automatically generates what? Motion. So now we can come up and have these devices called transformers. Now what determines the amount is the strength of the field. The number of conductor loops, because if you think about it, every little conductor puts out one of these when it's going in one direction. And if I keep looping them, I keep doing this, right? You understand? So every loop, if we wind them in the same direction, when I'm moving through the field in one direction, it acts like kind of like a DC source, and all these add together. So what determines the amount would be the number of conductor loops. And then 4 would be the speed of the motion. So we're not concerned. What determines the strength of the field would be what load you're going to put on the transformer. What determines the speed is the frequency, and we're using Alabama Power at 60 cycles. But I can control the what? Number of conductor loops. That means I come over here, the side of the transformer that points back toward the source, we call this the primary. The side of the transformer that points toward the load, we call this the secondary. And I can vary the ratio between the loops. Then we got to have something that couples the magnetic field. So we come up here and put an iron core, we put a core on there. Now the problem we have, if I use metal and I put a change in magnetic field through a metal, then it's going to try to induce a voltage into that metal. And if I put a big chunk of metal inside the transformer, then all that current adds up and we have a lot of current in what we call the core. So what they do to limit that amount of current and keep it from binding, what we use is what they call laminations, but it's a bunch of metal plates, and each one of them are insulated from each other by a real thin coat of paint. And what it does now is each little current that they call eddy current doesn't combine with the current next to it, right? You understand that? And what it does, it reduces the loss in the core. And I'll pass this around. So any transformer you can look at, and you can just about see the laminations, can't you? See them? So what we have is this is what we call an E-core. So there's a metal rod running down here, and the primary and the secondary are wound on top of each other. So they have a really, really good coefficient of coupling, right? Understand? And then what's the purpose of this? It's just to concentrate the magnetic field, right? You understand that? So if I didn't have something to concentrate the field, then I would get a lot of loss and my transformer wouldn't be efficient. Now we'll look at this. This is the primary right here. And then this is a multi-tap secondary. So we get a lot of different AC voltages off this. This is actually the transformer that came out of the trainer. Huh? Yeah, right on top of it. They wind right on top of each other. On this type of transformer right here, you'll see transformers will all have the primary and the secondary on the outsides too. Then three-phase transformers, they can't do like this. They can't do it like that because they're dealing with three phases. So three phases use a E-core, but they'll have one winding on the outside and one winding on the inside, and they'll be wrapped on top of each other. Okay. Now this is a very inefficient transformer. But what I have is I have this guy hooked up to my function generator. And then on this guy, all I have is just an LED. Let's see if I can point it up here. And then all I'm going to do is I'm going to come over here and just set this guy on top. So this is a transformer. So there's no electrical connection between these coils of wire, not at all, and this coil of wire right here. This is my primary. I have it hooked up to my power source. And all I'm doing, this is very inefficient, right? You understand that? I'm just laying this on top, and what happens to the LED? Turns on. Oh, so I'm magic, right? But that's just the basis of a transformer. It's very inefficient, right? You understand that? But that's the basis of a transformer. Just a bunch of coil of wire. So I'm putting AC through this thing. This does not pass DC. Transformers do not pass DC because we don't have what? We don't have motion. So I can use a transformer to step my voltage up for transmission, right? You understand that? So if I could step my voltage up to 750,000 volts, then I could send 750,000 watts of power with what? With 1 amp. So that's the advantage of AC. So AC we can transmit it over great distances by doing what? Stepping it up, right? And then start stepping it down. Now, what advantage does low voltage have over high voltage? Safer. That's the only reason. Safer. So in our house, we have a higher voltage. We have 240 and 120. What does 240 run? 240 runs all your high wattage appliances, right? You understand? 120 runs wall plugs, right? Where are you? 120 is either straight wired or the plugs have to be out of reach. So if you got an electric stove, where's the 240 plug at? It's down on the baseboard behind the stove. So what do you have to do to get to it? You have to pull your stove out, right? If you got a dryer, the plug is down. You can't get to it without pulling the dryer out. If you got a water heater, it's probably direct wired. If you got an HVA system, it's probably direct wired with some type of disconnect. So 240 is either direct wired or the plugs have to be down where you can't get to them easily, right? Then 120 is out there where you can hook it up. The problem is that your 120, you don't run high wattage devices on them, right? But you have to understand loads are designed around a certain current. So you can't take a load that's designed around 120 volts and hook it up to 240. What will it do? It'll burn it up instantly. Or you can't take a load that's designed to run on 240 and run it on 120 because it'll draw 1/4 of the power. So that's the advantage of AC. Plus, we can make electrical motors work off induction. So I can have a big chunk of metal that's got conductors in it, and I can put a magnetic field, and it works like a transformer. So I can induce a current into the thing that rotates, which generates a magnetic field. So the big advantage of AC is, number one, is AC motors are a lot less expensive because they can work off induction. Another advantage, of course, we can do we can transmit it. We can step it up for transmission, right, and step it down. But eventually, what advantage does DC have? We can store it, right, in batteries and stuff like that for later use. The biggest advantage is that we can electronically control it. We can take DC and we can convert it back into AC, but I don't have to do it at 60 cycles. I can do it at whatever frequencies that's available to me. So this device that we'll use every once in a while, we call this a function generator. And what can we do with the function generator? We can generate a frequency. We can change the voltage and we can change the frequency. Well, how do they do that? Well, they take AC. They take Alabama Power's AC, 120 volts AC. They convert it to DC. And once they get into DC, they can regenerate AC on basically any frequency that we want. Yeah, that's what we're going to learn right now. We're going to learn how we take AC and convert it into DC. We call these devices power supplies. Electronically, we can take DC and convert it back into AC. Electronically. But the problem is, what's nice is we transmit at a certain frequency. And why do we have to transmit at a certain frequency? Because the frequency sets the speed of our motors, but it also sets that magic thing called X of L equals 2 pi FL. So if Alabama Power was all over the place with their frequency, then F would be changing and the resistance of the transformer, the opposition of the transformer would be changing. So your power grid has to run at a precise frequency. You don't let that thing change, right? You understand that because of all your inductors you have up there. We have two primary frequencies used in the world. Over here we use 60 hertz. Over in Europe, their predominant frequency is 50 hertz. So over in Europe, if you ran an AC motor that was rated at a certain speed over here, if you ran it over there, it runs slower. Sure.
We're just walking through, Rich. I don't want to interrupt you.
But you are. You know you are, right, Tom?
Yes, sir. People say that to be nice.
If you want me to do something, it's time for a break anyway, okay?
I don't. We're just walking through.
Okay. So once we set this frequency right here with our power grid, we can't do what? We can't change it. But your stereo, what type of power system do you have in your car? You have a DC power system. Audio is not DC. Audio is what? AC. Well, how does your radio generate AC? Well, it does it what? Electronically. At a frequency that the radio controls, right? It's not. So that's what's nice about getting things into DC. My wife's, I think I told you, my wife has got a 120 volt plug in her van. Well, how do they get 120 volts? Well, they do it electronically through an inverter, right? You understand that? So you can go out to probably Walmart and buy an inverter for your car. You hook it up to your battery and it gives you AC. Well, that's what's nice about DC is we can electronically control it now, right? You understand? So I can turn DC back into AC if I want to. But when I turn it back into AC, I'm not controlled by Alabama Power anymore or TVA. I'm controlled with what I need for my application. Everybody understand that? So AC, if I could have a transformer designed around 400 cycles per second, it would be more efficient because the speed of the alternations are going up. So that means I don't need as many windings in my coil to get the right X of L. So if I could operate at a higher frequency, my transformers don't have to be as big. You understand that? Because they become more efficient. So we have a type of power supply we look at that's called a switch mode power supply, and that's what it does. It takes the DC right off the bat and does what? Reoscillates it at a lot higher frequency, and then my transformers are going to be little old tiny things because the transformers become a lot more efficient, right? You understand? But I can't have a transformer. We had The airplanes that I worked on in the Navy, they ran at 400 hertz. So I was going to make me a power supply, and I got a transformer, and I was going to make me a power supply, and I hooked it up to 60 cycle, and it melted. And why is that? Because it was designed for 400 hertz, and I didn't know it. So it was real funny, because I had it working, and I went off the shop, and I come back, and the whole shop was filled with smoke, and the transformer was bubbling. And the guys that was in the shop, they wasn't too happy about it. So we can't change these. So that's why the power grid, even though 400 hertz would be more efficient than 60 hertz, everything in the system is designed for what? 60. But a switch mode power supply does what? Takes a DC, re-oscillates it into a high frequency AC. Now everything can be a lot smaller. So these guys right here, these are switch mode power supplies. This guy right here is rated at 3.25 amps. If this was a linear power supply, it'd probably be about 3 times bigger than this, because the transformers would have to be so big. I'll have to bring my power supply. I got an 8 amp power supply that I built at the house. Well, let's take a 10-minute break, guys. Power supplies. What do they do? Right. This is the most common electronic circuit that's out there. So any device that's DC, it's got to have, that operates off of DC, it's got to have a power supply. So all your TVs, all your microwaves, all that kind of stuff, all your computers, all your cell phones, right? Tablets, stereos, are all what? They operate off DC. So that means we got to have, if it's not DC already available, then we have to have a power supply to convert to that. Well, even in a car. So a car, we have a power supply now. Because our generators are what? They're AC. Right? You understand that? And so somewhere there's got to be a power supply that takes that AC and converts it into the DC to even charge our batteries. So DC powers almost all electronic devices. A rectifier, this is the circuit that actually does what? It's a pulsating DC. And that's the problem. It puts out pulses because it's going to just, all the rectifier is going to do is just take those alternations that's coming from AC and just put them on one side, right? You understand? So you still have the pulses, and then we have to filter that out. Connects to a capacitor. We're going to connect to the capacitor. We can also do an inductor. The advantage of a capacitor is it's a lot cheaper than an inductor. This is going to come out and convert what we call pulsating DC into unregulated. So what do we mean by regulation, by the way? It's not a law, but in power supplies, what do we mean by regulation? If we regulate something, what does that mean? Yeah, and that's basically it. So with a DC, with a power supply, we want the output voltage to stay constant even though you're varying the loads, right? So normally if my load goes up, I require more current. My tendency of the output is to go down. Well, what a regulator is going to do is try to maintain a constant output, as long as you stay within the limits of the regulator. So this is the basic makeup of a power supply. So we're going to start off with this. We're going to come up and have a transformer. We're not going to plug it into the wall. We're going to go into a transformer because we're not going to deal with 120 volts. And we're going to use our transformer to do what? To step it down, right? Understand? We're going to use a transformer that's inside the trainer. So there's a trainer. We'll try to take one of the trainers apart so y'all can see all the parts of the power supply as we move along. And then what we do is we'll come up here. So out of the rectifier, we get pulsating DC. This would be what we get out of what we call a half-wave rectifier. A half-wave rectifier only gives you one alternation. A full wave rectifier somehow is going to steer both alternations either to a positive or to a negative, depending on what type of power supply you need. Okay? So this is where we'll start off with. Of course, like I said, we're not going to plug ours in. We're going to have what over here? Yeah, we'll come up with, we're going to have a transformer. And we're going to have what we call a step-down transformer. Everybody okay with that means? It means it's going to take the voltage and step it down. We're going to use a 12.6 volt transformer. Center tap, which we'll talk about in a minute. And this is on the trainer. This transformer I have is a 12.6 volt center tap transformer. I'm not going to use the trainer. I'm going to actually use a real trainer. Let y'all see that. I was going to say real transformer. There's a real transformer in the trainer. It's just that it's covered up, right, inside the case. And like I said, we'll pop one of these things apart and look as we go through these parts of power supply. So what the rectifier does is it takes the AC and converts it into what we call pulsating DC. Everybody okay? Now my load is going to see the average of this. We'll look at that. We've already talked about that last class, right? This will work good with devices like motors. Works great with devices. It's very simple, very cheap, right? You understand? Light bulbs and stuff like that. LEDs would work fine off this. But electronic devices wouldn't. So then what we're going to do is we're going to take the output of this and we're going to run it through what we call a what? Filter. And what this is going to do, it's going to convert this into unregulated DC. So it's going to have these pulses riding across the top. And if I come up here and put a load over here, these guys will actually get bigger. If I take the load away, it'll go down. It'll go down. So we call this unregulated DC. So what happens is my average output voltage is going to change with load. And then we'll run this through a what? A regulator, which is going to set the output voltage. So what we'll do is we'll look at this lower trough, and then we'll regulate below this. We'll show you that when we get there. So regulator, what it's going to do is try to maintain a constant output even though I vary my loads. But it's only going to be over a certain range, right? You understand? It's just like I've got my cruise control on my car or my vehicle. You know, if I'm on a flat surface and you got it set on 75, it'll set on 75. You go up a hill, now the gas goes down, and it don't downshift, right? You understand? And then what happens to your speed? It goes down because you've exceeded the what? How that thing can regulate it. And you go down a hill like this, and you got it set at 75. Odds are it's going to go above that, right? You understand? Because you've exceeded the range of what that regulation does. So that's a regulator right there. Your speed control is a pretty good example of a regulator. So even though you're going through varying positions, your regulator tries to do what? It tries to maintain a constant speed even though you go through varying positions. But if you exceed the range capabilities of it, then it goes out of regulation. So one of the things we need to understand about a power supply, as long as you don't exceed the regulation. So this guy here says it'll regulate with an input voltage between, these guys are really neat because they're switching power supplies. I'm trying to find the input voltage. Input can be anywhere between 100 volts and 240 volts. My output is going to be 20 volts, up to 3.25 amps. So if I tried to get over 3.25 amps out, then the output's probably going to do what? It's going to go down. If my input gets out of that voltage range, the output would probably go down. So this is pretty neat. These are switching power supplies. Normally switching power supplies has a real wide voltage range you can input on them, where this power supply, this is the layout of what we call a linear power supply. These guys are easy to design, and easy to troubleshoot, but they're big, right? You understand? They're inefficient. Switching power supplies, they're very efficient, but they're almost impossible to troubleshoot. So that's why they sell them up. So normally if a switching power supply goes bad, even if I had a switching power supply that went bad, I'd change it out. If I had a linear power supply, then I would fix it, like I do on these trainers. A regulator circuit that maintains an almost constant DC output voltage to the load with varying inputs. So we can have if I was to measure my 120 volts right here, and then I was to go home and measure my 120 volts at house, but would both of them be exactly 120 volts? No way. Because it's going through wires, right? A transformer can't regulate. All a transformer can pass what it gives. So it varied in fact, it would vary during the day. During heavy loads, my 120 volts would be a little less. At night, it would probably be a little more, right? You understand, because of the amount of current the wires are trying. Alabama Power regulates the voltage, but they regulate it at the plant, right? Everybody understand that? So regulators in power supplies have to do two things. It's got to maintain a constant output, even though my input voltage varies, right? You understand? So I can plug it in over here. I get 5 volts. I can go over there to A building and have 5 volts, even though if I looked at these two voltages, they would be a little different. And then with varying loads. So I can put a 100 ohm resistor on here, or I can put a 1,000 ohm resistor on here, and it should still be around 5 volts if I've got a 5 volt regulated power supply. Are you understand? Regulators can consist of power supply regulators have been around for years. So it makes sense that they're going to start integrating these things onto one piece of silicon, right? You understand? So we have regulator integrated circuits. We have what we call fixed regulators, which means those are designed to give us a voltage output. So I can buy a 5 volt regulator, a 12 volt regulator, a 15 volt regulator, right? You understand? I can buy a minus 5 volt regulator, minus 12 volt regulator, right? You understand that? And then we have what we call variable regulators. And what does a variable regulator give us the ability to do? Vary the output voltage, yeah. So our trainers have variable regulators on. So we get on those trainers, we got 2 little knobs, we can do what? We can turn, we can vary. So we have those in integrated circuits too. We have variable regulators in integrated circuits, and we'll show you how to do it with discrete components, and then you understand, well, heck, they could integrate this on a single thing. So most of your regulators now, except for very simple ones, are integrated circuits. So unregulated power supplies, guys, this is where we're going to start out at. And this is what we're looking at. So this is the actual calculus form for figuring the average output. 1 over pi, the interval between 0 and pi, VP times the sine. So that's the actual math formula. Are we going to use that? No. Or we could use V average is equal to V peak over pi times the cosine of that theta. Right? Raised to the pi power. Are we going to use that one? No. This is the guy we're going to use right here. 2V peak over pi.
So now where did you go?
Huh?
What is going to end up here?
2V peak over pi. Now what this does is this gives us the average DC value of an alternation. So the average DC value of this alternation is 2V peak over pi. Do y'all understand that formula? So V peak would be whatever that value is right there, right? You understand? And you can use the positive or the negative. It don't make any difference because they're mirror images of each other. It's just that if you use the positive and we're using the negative, you just put negative out there, right? You understand? 2V peak over pi. Everybody okay?
It's the same with VP, right?
No.
It's not.
This is peak to peak. If I was going to come up here and measure, this, This voltage right here we call VP. This voltage right here we call VP. So V peak to peak would be twice VP. But when you convert it to DC, you're only dealing with one. You're not dealing with V peak to peak, right? You understand? Even if I come over here and do this later on, that's still dealing with peak. It's not dealing with peak to peak, right? You understand that? Yeah, but that's the point. I understand what you're saying. But what we're trying to do is the average value of an alternation is actually, that's a little low, guys. If you did all this math up here, it would come up and give you 0.637 or 63.7%. Well, if you come over here and you take 2, so let's move the V peak over here because it's on top. If I take 2 and divide it by pi, guess what it'll always come up again? 0.36. You understand, or close to that. So instead of me trying to memorize this fraction, which is fine, to me 2 over pi is, so it's not 2 times V peak, it's actually 2 over pi, and then we multiply that by V peak. So that make a little more sense? Yeah. So you're exactly right. Are we okay? Huh? Now what we're going to do is we're going to start off with what we call a half wave, which means we're not going to have this right here. So what that means is on a half wave, what I'm going to end up with is I'm going to strip off one of the alternations, and then we will have this alternation again. Now this gives me, this guy gives me an average of 2 V peak over pi, or 2 divided by pi over V peak, or times V peak. But the problem is this is average with what? It's average with 0. So on half wave, what we're going to do is just drop off the 2. So half wave, my DC average on half wave is going to be equal to V. It's going to be equal to V peak over pi. You understand why? Because what are we going to do? We're losing that 0. So if I took V peak, 2 V peak over pi and averaged that with 0, then that just means we just dropped the 2, right? Everybody okay? So somewhere on your formula sheet, you should see that for DC, and then of course I think I put the DC, and then I put like HW, AVG, HW or something like that. So that's the formula you'll use for what? Half wave. Are we okay? So this is a circle list. What's that? Up at the top. So all our power supply formulas are on the very top of the front. Yeah, see that? Half wave. See where so HW stands for half wave and FW stands for full wave. So a half wave rectifier, this is what's so key. It consists of an AC voltage source, diode, and load. The diode anode is pointing toward the AC source. We end up with a positive supply. If the cathode is pointing toward it, we end up with a negative supply. So that's the first thing we're going to do, decide if it's positive or negative, right? Everybody okay? Now normally our AC, when the diode, so when the cathode is pointing toward the voltage source, we get a negative. If the anode is pointing toward the voltage source, we get a positive. Everybody okay? Now, why would we need both AC and negative? Why would we need both positive and negative supplies? Positive supplies are the predominant one, but why would I ever need a negative and a positive supply? Oh, you're thinking another thing. I didn't hear what he said. He said sinking resources, but that's not it. Well, this function generator generates AC. You understand that? Well, to generate AC, I have to have a positive AC a positive DC supply to generate the positive alternation, and I have to have a what? A negative DC supply to generate a negative alternation. So your stereo in your car takes that DC of one polarity and converts it into a DC of a plus and a minus. So normally we use a negative power supply if we're going to deal with audio or try to get back to AC, right? You understand that? Then our predominant power supply is a positive. Only the positive half cycle of the AC input is across the load. So this is what we come up and get right here. If I have an AC voltage source, I hook it up, right? So that's the symbol of an AC voltage source. Everybody okay? Right? So when this is going through the positive alternation, that's going to put a positive toward the anode. It's going to point the negative toward the cathode, and this guy's going to forward bias. It comes up here, current goes through here, comes up through here, goes back, makes the bottom of the resistor, the load negative, and it makes the top of the resistor positive. So this is a positive supply, right? You understand that? Now what we're going to find out is my output is going to be about 0.7 of a volt less than my input. So over here, if the peak was 10 volts, then over here we would have about 9.3. Because it took 0.7 of a volt to turn the diode on, right? You understand that? And I think I overlaid them last time, so you can actually see the output pulse was slightly lower than the what? The input. Then during the negative alternation, then what would that do? That would put a negative on the that would put a negative on the anode, that would put a positive on the cathode, and what does the diode do? Turns off. So if we had an oscilloscope looking across the diode would be doing that. If I looked across the load, it's going to be what? 0. Because the diode turns off. It does this electronically. It does it instantly, right? You understand that? And that's what's neat. So if I could flip a switch at 60 times a second, I could create pulsating DC if I was synchronized. This guy here turns off and on electronically, right? You understand that? Everybody okay? So what we end up with, if I looked at the output with an oscilloscope, is I would see this right here. Right? Everybody okay? So I have a breadboard. What do we use breadboards for? Yeah, to basically build circuits to test them out. Almost all electronic circuits that I've ever seen is first put together on a breadboard. Because if you want to make changes, all you have to do is just move things around, right? And everybody knows how the breadboard works. Are you okay? Huh? Yeah, y'all have to do it. I'm not going to do it. We're only dealing with 12.6 volts, which is well below the limit, and we're only dealing with half of that. So I'm going to flip mine around up here without turning it on. But I don't want to see y'all do it. So everybody understand the breadboard. So how does the breadboard work? Yeah, if I want something connected together, I hook it in the same vertical line. If I don't want it connected together, I hook it in a different vertical line, right? You understand? We'll see that. We have a break right here, which basically, wrong side, this break right here separates this vertical line from this vertical line. But okay. So I'm going to get a diode. What do I do with my diode? I don't want that one. Oh, here it is. By the way, this is an amplifier right here. These are transistors. So I'm going to come over here and I'm going to take this and plug it in here. And then I have to have a load. We'll just use, here's a yellow, violet, orange. Not 50. Yeah, I love 47K. Okay, so here's my transformer. And this is what we call a center tap transformer. This is a 12.6 center tap transformer. So that means if I come across the two outsides, I would get 12.6 volts approximately. On mine, it's the two blue ones. If I go between, if I go to that one to this one, I get 6.3 volts. Everybody understand that? Well, we've only got one blue wire. Don't look at my connection. So all this is right here is it so I can plug it into the breadboard. Normally the wires on the transformer are stranded wire. And what's the big advantage of stranded wire over solid state wire? It's very flexible. So the big advantage of stranded wire over solid state wire is flexible. The biggest advantage of solid strand wire is easier to terminate. So on this, if I wanted, I wouldn't twist the wires together and put them on a wire nut. I would solder them. This right here, though, if you want to splice them, you can twist them together, right? You understand? If I wanted to, I could stick this under a screw and wrap it around the screw, right? You understand? If this was stranded wire and we wanted to put it a screw, we'd have to put a terminal on it. That makes sense? So the advantage of stranded wire is that it's very flexible. The advantage of solid strand is that it's easier to terminate and it's easier to splice. So we're going to use 1/2 of it. So I'm going to use 6.3 volts. So this would be the symbol of a center tap transformer. So what we got, and ours is a step down. So we'd have more turns in the primary than we do the secondary. And then this would indicate that's the laminated core. And then over here I would do this. And then I have another wire that comes out exactly in the center. Everybody okay? This is what's on your house. So if I go across this, then I get the full voltage of the transformer. So when we say 12 volt, so that's the way this transformer is rated, 12 VCT, which is telling me it's a center tap transformer. So your house, this is where you get 240 at. That's your 240. And what do we get between here and here? That's where we get our 120. So it's one transformer, it's just a center tap transformer. And that's why you have 3 wires on your down prop. What they do is they take the center tap and they reference it to earth ground. So that's why it's going to be the metal, it's going to be exposed because there's no potential relative to ground. So you've ever looked at the down drop on it's got 2 wires that are insulated, right? And then it's got another wire that the other 2 wires are wrapped around. That's the center tap, the one that's wrapped around the center tap. We're dealing with a 12.6 volts, 12.6 volt center tap. So that means if I go all the way across, I should get around 12.6. If I go across here, then I should get around 6.3 volts. Everybody okay? That makes sense? Everybody okay? And that's what's up on your power pole, or if you're lucky enough to live in a neighborhood where they bury all the power, then that's what's in those big old boxes every once in a while, is those big transformers. We're just going to do 6.3 volts. Now that 6.3 is an average because it's going to be given at a current. So this guy here is rated at, I don't see the current on it, 1 amp. So it means if I draw below 1 amp, it's going to output a little more than 6.3 volts. If I draw above it, it's going to be below that, right? So we'll measure it and see because that's what we need for our calculations. So here's my circuit. So I have my diode. Okay, we'll make a positive supply first. So what I'm going to do is, here's my diode, here's my load. Y'all see that? Here's my 4.7K, my 47K. Here's my diode. It's a 1N 4001. It has a breakover voltage around 50 volts, so should be okay, right? Everybody okay? Then I'm gonna take my center tap and I'm gonna hook it over here to my load side. And we could hook it up backwards. And I'm gonna hook this one up right there. Are we okay? Now I've got the cathode pointing back to, I got the anode pointing back toward the source. Can y'all see the little silver stripe right there? Yeah. So I've got my anode pointing back toward my power source, so this would be a positive supply. Everybody okay so far? Yeah, so here's the metal. You can't see it, it's right there. And so this is in the same line. These are connected together. Then I come over here to another vertical line, so that means this is not connected to that. We'll see it all the time where they'll come up here and they'll put a resistor in the same line. I could go across this gap, right? You understand? Everybody okay? So my schematic, I was going to draw the schematic for this circuit. Then it would look like this. I would come over here and I would have my transformer, right? And it's a center tap transformer, but we don't have, but we're using this, right? Everybody okay? This right here is going to be my common. Then I come over here, I have my diode like this. And then I have my resistor right there connected to common, and it's a 47K. That's the schematic. Now notice the anode is pointing toward the what? Toward the source. So we should end up with exactly what they're showing us right now. If we look at it on the scope, if I measure it in a meter, then it's going to measure the DC average, right? You understand? So to see this, if we want to see this, then we're going to have to look at it on the scope. So I'm going to take my scope, look it up. I consider this to be my common, so I'm going to put my black lead there. And then I'm going to come over here and take my other lead right here. Then I'm going to take my other scope probe. And since this is only 60 cycles, guys, we don't have to hook up this common because we've already got a common, right? All right. And then we're going to come up here and throw power on this thing. There's my plug. And I'm going to plug it in. Here's my oscilloscope. Now what's going on? Well, the problem is I'm taking something over here that's snapping pictures. Right, you understand? And then I'm going to come over here on something that's displaying it, and they're not in sync with each other. So right now my scope is not in sync with the waveform. So to synchronize it, what we do is over here on our scope, we have something called a trigger. And that's what we're going to do. To trigger this, what we're going to do is we're going to reference this to one of these edges. So now instead of just doing this kind of stuff, when this goes positive, this guy here is going to trigger it, so they're going to be doing what? They're going to be synchronizing. So what we do on an oscilloscope, and so your TV, your TV's doing this, but what they do in the video is they put the synchronizing signals when the camera automatically puts the synchronizing signals in the video, right? Here we don't have a synchronizing signal, so we're going to have to synchronize to the waveform. So I'm going to come over here on my trigger menu. I'll look at the source. What's my source? Channel 1, right? Which is 1. So I'm going to synchronize with this guy, with my yellow. Okay. It says, let me bring it back up. It says I'm looking for the rising edge, and I'm looking for an edge. So what I get you to do now is, if you look, I have a line on this that shows me what voltage I want to synchronize with. So notice as soon as I get that white line down into my waveform, it should come up here and freeze. See that? And of course now I'm got my scope going too fast. I'm gonna come in here and I'm gonna turn down my speed. And there's my halfway. It looks like we might be on AC. Let me look at my coupling. Can you notice this right here's got a little slant to it? You see that? That's not slanted, guys. What we do is your scope has got two types of ways we can couple it. We can use what we call AC coupling and what we call DC coupling. A lot of people get that confused with measuring AC and measuring DC. 99.9% of the time we use DC coupling. No matter what we measure, right? So I'm going to go on A, and they do have DC coupling. Now, see what happened when I went to AC? Of course, that's a ground reference. I don't know why it's slanted a little bit. It shouldn't be. So this is our output. Let's bring up our other channel. And what can y'all see? Notice my blue is slightly higher than my white. And here's the negative alternation. What do we see about a negative? It's just what? It's just clipped off. No, not the negative. Here's the yellow.
Okay.
Here's the AC. So this is what's actually coming into the rectifier. So what did it do with the negative alternation? It just clipped it off. What did it do with the positive alternation? It let it come through, but it's what? It's ever so slightly less than what's coming in. Because what did we lose? We lost that 0.7 of a volt, turn the diode on, right? You understand? Everybody okay? So here's our peak. Let's see if I can get it. I don't think I can get it any bigger. I'll go off the screen. So here's my peak. It's measuring, I've got it on 5 volts per division. So I've got 5, 10, 15, 20 volts. Peak. Well, the transformer said 6.3 volts. Huh? Yeah, well, it's not an average. We shouldn't use the term average, but you're right. The problem with this, so here's my meter right here. I'm going to turn it on, right? And this is what you got to understand. I'm going to come over here and I'm going to turn it on. And I'm going to come over here and I'm going to put it on AC. Where's my AC volts at? Right here. I'm going to put it on 440 volts. And I'm going to take this thing and I'm going to put it into this outlet right here. And it's measuring, we got about 114 volts there. I'm going to take this meter and I'm going to put it on DC. Here's AC. Right. Here's AC. Here's DC. This is the average right here. This is the average. This is the DC average of a cycle. The DC average of a cycle is 0. Y'all see that? This gets people in trouble, right? That's when I like this meter better, where you have an AC range and a DC range. Some of your meters, you got a push button that you got to switch it between what? AC and DC. And a lot of people forget that, right? So I get over here on this wall outlet, on this switch, and I measure on it, measure 0, and I don't make sure it's on AC, right? You understand? I stick my hand in there, I get shocked. I don't like that. But that's just the way you got to get used to it. So this is an average right here. So it means if I want to figure out the work AC produces, when the negative does not cancel out the positive, Then we got to come up with another method, and we don't call it the average, we call it the effective voltage, right? You understand? And how do we do that? We did that last class. What do we call it? Huh? 0.707. It's actually what we call the root mean square, right? You understand? RMS. So when they give you a voltage and they don't specify what it is, so if I'm going to say peak voltage, I'm going to put V peak, right? You understand? If I put 120 volts AC, then what is that? That's RMS, right? You understand? So that 6.3 volts is what? It's RMS. So how would I find out what the peak value is? So if VRMS is equal to V, for a sine wave, it's going to always be 70.7%, right? Or 0.707. So if my formula for this is this, then how would I rearrange that to solve for VP? Yeah, it's going to be VRMS divided by 0.707. So, right, so I would say 6.3 divided by 0.707. This gives me VP. So what would that give me? Get your calculator out for me. Okay, so that's 8.9, right? Or around 9 volts, right? Now this is V peak. My scope don't measure V peak. My scope measures V peak peak. So I would take this times 2. So V peak peak should be around what? 18 volts, V peak. We're measuring about 20. Which means what? Is something bad? No. It's just that the transformer's not putting out exactly 6.3 volts. Because we're not loading it, right? You understand? We might not have, this guy, we see some transformers rated at 110 volts. So normally the transformer will measure higher than what it's rated. So we got 20 volts peak peak. Okay. So that means we got 10 volts peak, right? Everybody okay? Everybody okay? So my VRMS, my anticipated voltage, my anticipated DC average should be equal to what? 9.3 divided by pi. Everybody understand that? Huh? Well, when I measured peak to peak, I measured it over here. I measured it on the input. So when I measured V peak, I measured it here over on the input. And notice the input is about 7/10 higher than the what? Than what's across my load. So 10 minus 7.3, 7/10 is 9.3. Then we divide that pi by pi because we're dealing with a half-wave rectifier, right? You understand that? Okay, Anthony? We're going to look and see what work we're going to get out of this. We don't get peak work. We get the average work out of this, right? You understand? Everybody understand? Now I could use the 0.637, but you can't use 0.637 because that's for one alternation, and I would average that with 0, right? You understand? So you'd have to take the 0.637, divide it by 2, and then use that, right? Or you can use V peak over pi for half wave, and we'll use 2 V peak over pi for full wave. Whichever one's easiest for you to remember. I like the 2 V peak over pi. Oops. I keep doing it. Oh, I can't do it. This guy here don't like to give up control. So I'm going to say 10 is VP. I'm going to take 9.3 divided by pi, and what do we get? 2.96. So I would run anything rated at 3 volts on this power supply. I could run a 3-volt motor running on this. I could take a light bulb that's rated for 3 volts, and I could run it on this, right? You understand? Got a circuit. So let's see. So I'm going to take my meter. So now we've got rid of the negative alternation. So now my meter should measure on DC. So this is DC, right? You understand? This is not going below AC. So I'm going to take my meter. I'm going to flop it over. And then I'm going to come over here. And let's put it full screen. And I'm going to take my meter leads out of this 120 volts. And then I'm going to put it across my load. I've got my meter on DC, right? I'm going to put it on the 4-volt scale, and I'm going to put it across my load. And it measures 3 volts. Calculated what? 3.9. I'm sorry, 2.9. This measures 3 volts. Yeah, it's across the load. That's not the resistance of the load. That's the voltage across the load.
What's the load? You said measure across the load.
The load is that 4.7, that 47K that we put on the output. That's what I measure. If I measure across here, if I measure across the circuit, what's it going to show? It's going to show me 0 because I got my meter on. Yeah, I got my meter on DC, right? You understand? If I measure across the load, this is DC now. Ain't that neat? So we calculated we get what? 2.9 something, and we're measuring almost that. Right? You understand? What would be the difference? Well, we got a 47K on. We're not loading this down much, right? You understand that? And then plus the diode is not dropping exactly 17 minutes. Right? So if I was to use 6.3, instead of measuring it like we did, if I was to use 6.3, we might have came up with 2.5 volts, and I measured 3, that's going to be fine. So normally we don't measure the output of the transformer. We take what the transformer says it's going to be. And we understand there's a 99% chance that if it's a 6.3 volt transformer, it's not going to be 6.3. Because that all depends on what type of load you're putting on your transformer. Normally we don't run transformers at their maximum load, so normally they'll put out more voltage than what they're rated at. What do you mean? We could have used the bottom, or we could have used this AC, guys. As long as one of these guys are not referenced to ground, it don't make any difference. I could come up here, I could swap these around. Because I'm setting up the ground reference, right? And we'd get the same thing, right? It would work the same way, right? But you got to be careful, like your power pole, that center tap is referenced to ground. So you would have to reference, you could use it all the way across and not reference it to ground, right? You understand? Not use ground. So 240, the power does not use ground, even though you bring ground out to, you hook it up to the chassis of the metal to keep your water heater becoming electrically hot, right? If something happens. So, but 240 is not referenced to ground. 120 is, right? You understand that? So all your 240 devices, the loads themselves are not referenced to ground. So if I'm going to come up here, so this is a I disconnected my. So I'm going to bring my scope back up here. And I'm going to turn off channel 2, just to avoid a little bit of confusion. Turn off channel 2. And then what I'm going to do is I'm going to come over and take my diode, and I'm going to swap it around. Just 3 volts there, guys. So now what I've done is I've turned my cathode toward the load, and I've got a negative power supply. Now I've gone out of trigger because my trigger is up here, right? So I'm gonna bring my reference down here, put it inside this, and it should freeze it. And now this would be a negative power supply. What should it measure? A negative 3 volts, right? You understand that? So we come over here, use the same reference that I got my scope onto, and now we have a negative DC supply. But look, you know, see, it measures about what? I'll get it in a minute. Measures the same, but now it's showing what? Negative. So what determines whether you have a negative or positive DC supplies depends on the reference of the diode. If the cathode's point, so notice my cathode is pointing toward the thing now, pointing toward the source. My cathode is pointing toward the source, so I have a negative supply. Yeah. Well, no, it's not reverse bias. We can't say it's reverse bias. It's reverse bias. It reverse biases during the positive alternation, but it's forward bias during the negative alternations, right? Understand? If it was reverse bias, it would be off, period. So what we're doing now is we're reverse biasing it here, right? You understand? It's forward biased here.
So right now, if you took the AC alternation and swap it out, then would be reverse bias.
What do you mean?
If you took the ground and put it
Now, it's AC, guys. Okay, so let's swap them around. Let's answer your question. I'm gonna swap these leads around. I'm gonna come over here and I'm gonna swap these leads around.
Is it for that time?
We get the same thing. We're still blocking the negative alternations and passing. We're blocking the positive alternations and passing the negative alternations. Right? Y'all understand? It's AC. AC varies as what? Polarity. So the diode is going to be forward biased during one alternation and reverse biased during the other, and it don't make any difference which side you put up there. I mean, I've got an AC source, and what does an AC source do? It changes polarity. Right? You understand that? So what happens if I come over here? What happens is now I have my diode pointing like this. I'm not going to draw the transformer. I'm just going to draw an AC source. Okay, so I got my diode pointed like this. And here's my load. Right? So is it forward bias or reverse bias? Well, when this right here is on a positive alternation, that's positive, that negative, the sucker cuts off. But what happens? So that would be during this alternation, but now it drops down to 0. Now what does it do? It swaps polarity. So this right here goes to minus, this right here goes to plus, it's forward bias. And now current gets to flow, but now current is flowing in this direction right here. So the top of my resistor is negative, the bottom of my resistor is positive. But you don't have to sit there and figure out current flow. You just say, okay, if the cathode is pointing toward the source, I'm going to get negative pulses. If the anode is pointing toward the source, I'm going to get what? Positive circuit. Just because I swap the diode around, it's not, you can't say it's reverse bias, because what are we putting on it? We're putting AC.
So I guess that's why we were saying reverse bias, cut it off, just when it's in the reverse bias. It don't alternate right back to the
Yeah, I mean, if I was to come up here and put this, if I was going to come up here and put this on a DC source, that's what you're trying to see. A DC source don't change polarity unless you change the battery around, right? But if I was to take a battery and I was to sit here and do it that, then one direction it would be what? Forward bias. The other direction it would be what? Reverse bias. But on AC, we don't have to sit here and do that, because it's what? It automatically reverses bias. It don't make any difference which side of the transformer you use. All you got to be is real careful what they do. So Alabama Power, what they do is, so now one thing about a transformer is that you lose your ground reference when you go through the transformer. Because I'm not transferring it relative to ground, I'm transferring it relative to a magnetic field, right? You understand? If you want your output to be grounded, you have to reestablish ground on the other side of that transformer. So what do you see on the power pole? What do? Somewhere on your house is a rod driven in ground, and they hook that up to that center wire, and they reestablish the ground on the other side of that transformer, right? You understand? A lot of times they transfer power without a ground lead, and then they reestablish the ground where on the output side. So that's what you got to figure out. So our trainers, if you look at this power supply, they don't call the black lead ground, they call it common. So on the output of these DC power supplies, it's not referenced to ground. And now it's got a green thing on the back, right? That if you want it referenced to ground, you'd bring a wire around and hook it up. And now what's the advantage of not being referenced to ground? Well, you can set any ground we want to, right? You understand? Or we don't have to worry about getting shocked between there and ground. So if I have something that's not referenced to ground through a transformer, I could literally touch ground and touch an AC circuit, and it's not going to bother me at all, believe that or not. But the problem is now we got a problem with things building up static charges in relative to ground. The problem is most of our appliances have metal chassis on them, right? So that's a conductor. And I put AC on that, and a magnetic field strikes that metal, it'll induce a voltage in that metal. If I don't get that up, then those devices will handle a charge relative to ground. Right? You understand that? So that's why in houses we reference things to ground, so that way I can ground the chassis, and if one of my lines get in contact with that chassis, what will it do? It'll pop your breaker, or blow your breaker, or blow a fuse. But I've seen situations where we don't want things to be ground. We isolate it. So a transformer can isolate. It can strip off the ground reference for you if you need to. Like on this oscilloscope, it's referenced to ground. So as soon as I came up and did this, put that little old wire right there, then now this guy is referenced to ground. But it's up to me, right? You understand? I could have just well put the ground lead up here at the top of my diode. But now I can't take this guy and put it right there. If I take that and put it right there, I've got a short circuit, right? You understand? So that's the big difference between an oscilloscope and a meter. The black lead on this meter, this guy is not referenced to anything. And we don't call this ground, we call this meter common. This is where your meter makes measurements relative to it. So where can you put this black lead in a circuit? Anywhere. Where you can put this lead in a circuit. If it's a grounded circuit, you got one place you can put it, and that's on ground. That's it. You can't move this inside the circuit. So that's a big difference between an oscilloscope and a meter. An oscilloscope, this lead is referenced to earth ground, unless I plug my oscilloscope into an isolation transformer. And as soon as I plug it into an isolation transformer, then what do? We strip the ground off, and then I can put this black lead anywhere I want to. But you have to be careful. So out at US Steel, we had to measure things, and we had an oscilloscope. So the chassis of the oscilloscope could become electrically hot, right? You understand that? But we had to measure some big SCR drives and stuff, and we had to move the ground. We had to move that black lead around, so we ran it through an isolation transformer. But they put it inside a Marcotta box, which is an insulator, and we use insulated gloves every time we use that oscilloscope. So y'all understand that? That's a normal tendency. You say, I'm going to switch the diode around. It's normal tendency to say, well, now it's what? Reverse bias. But it's AC. Y'all understand? So what the direction of the diode determines what? Whether we get a negative DC power supply or whether we get a positive DC power. Okay, guys, let's take a break. 10 minutes. Last one, right? All the way across the transformer, what DC voltage should I get out of this thing? Calculate it. That's a good guess. But y'all, we want y'all to do the math. Hopefully it comes up to be around 6, right?
Sorry, Rick, one more interruption.
Those resistors. And you calculated with the measured value instead of the color-coded value because you're just trying to prove that V is equal to I times R, right? And I, y'all understand that. After that class, guys, we don't worry about measuring resistors. What we do is we use their color-coded value, and we know if I use their color-coded value, then my calculations and my measured are not going to be the same. But they're going to be what? They're going to be close. So even though that I know this guy's putting out more than 12.6 volts, right? You understand? I'm going to use 12.6 volts to do my calculation. I hope not. It should come up to be pretty close to 6. So let's say 12.6, right? You understand? So the first thing I need to do is convert that into VP because all our formulas on power supplies deal with VP. So I'm going to say 12.6 and I'm going to divide that by what? 0.707. So that gives us what? 17.8, right? And then my DC, my volts DC is going to be, or DCV, I should put that. It should be about 17.8 divided by pi. Yeah, 5.67 volts. So we know we're going to measure about 6, right? But what we're saying is that when I do my calculations, I use the values that are given to me. I don't go out and measure the output of my transformer, right? You understand that. I take for granted what's given to me. So here I'm going to go all the way across the thing. So I'm going to take off this guy right here. I'm going to come over and get this guy right here. Be careful not to touch. Put it right there. And then I'm going to take my meter and put it on the 40 volt scale because I know what I'm expecting to see. And I'm going to measure across the circuit. And it measures 6.27 volts. Not bad, right? And what's the difference? Well, we're taking for granted that we forgot to take out 7/10 of a volt too. And it's minus. Why is it minus? You can't say it's backwards. Because backwards is a relative term, right? Because the cathode is pointing towards the source. So we've created a negative power supply, right? If I come up here and swap the diode around, I'm going to turn the anode toward the source. So my anode is pointing toward the source, and I come up here and measure this. Now it's going to measure positive, but it should be the same thing. See that? So these are halfway rectifiers. Really cool. Very cheap. All you need, I could hook this thing, as long as the breakover voltage for my diode was, I could take these and hook it right across 120 volt source. What DC would I get out of that? 120 volts. What DC should I expect to get out of that? Of course, 120 volts is also relative. No, I'm looking at DC. You're thinking AC, I'm looking at DC. Right? So I took 120 divided by 0.707, divided that by pi. So there's 54 volts DC right there, just by taking a diode and hooking it in series with 120 volts. But I'd have to make sure that it's got a break. What would the breakover rating of it be? Yeah, what would it break over? What type of breakover rating what would be the minimum? Of course, close. Not peak, because we're only blocking one alternation. This guy right here, y'all hear what Anthony said? He said about 170 volts, which would be about right, but we're not going to go at 100. We're going to be a lot more, because what we're doing is we're passing one alternation and we're blocking the other. The peak-to-peak value of 120 volts is around 370 volts. No, I'm sorry, 340 volts. Peak-to-peak. We cut off that one. That diode's got to drop this. Not the average. That diode has got to block 170 volts. Right? You understand? So this is why it's important to be able to go between, understand peak, and that breakover voltage is a DC voltage, right? And that's what it's seeing this. It's seeing this guy right there, right? And if you exceed that, it'll break it over. Now, we're not going to do 170 volts. For one thing, odds are it's not going to be that anyway, right? It's not going to be 120 volts. So we'd probably use one that had a breakover voltage of maybe 200 or 300 volts. Probably 300 volts, because even 170 volts is close. Even 200 volts is close to what? 170. So probably, 500 volt breakover we'd use to rectify 120 volts. And that's why it's important to be able to go between peaks. So these are maximum values, and this guy sees that. So yeah, okay. So I could go over and get like a 4007 if we got one over there, and I could hook this up directly to Alabama Power without going through anything, right? You understand that? Of course, it'd be dangerous. It's touching stuff, but I could run a load rated at a DC load rated at 50 volts, 54 volts, or 60 volts. Without any problem. So halfway, we okay? So the average of a full wave is this. Then we have to divide it by 2. Now this is full wave. So full wave, I'm going to take the other alternation that we blocked, and somehow I'm going to guide it up to the other side. Okay? Everybody understand?
He's saying the one that we block off, we'll bring it up.
With a diode. That's what we can do with a diode. Now the first one we're going to look at requires a center tap transformer. So what we're going to do on this guy is I'm going to put a diode up here. Let's do a positive supply first. And I'm going to put a diode down here. And then on this side, I'm going to connect them together. Then I'm going to put a load. And what I'm going to do is this is going to be the common of my load. And this is going to be the common of, so I'm going to use the center tap, it's going to be the common of the circuit. Everybody okay? So what happens, now let's just look at this as DC. So what happens when this is positive, this is negative in respect to that positive. This is positive in respect to that right there. Y'all understand that? Yes or no? It's not a ground, it's a common. I can make it a ground if I wanted to. But we're dealing with a common here.
I thought it was ground from the transformer.
No, our transformers are isolated.
Okay.
That transformer right here, it might be over on this side, then over on this side is neutral. This guy here on the primary side, neutral is reference to ground. As soon as I go through that transformer, we're on the secondary side of the transformer. The only way ground gets on the other side is if what? You make it. So here we're definitely using a common. And we'll see that in a minute. When we go through the other way, we call it a bridge. We can't use ground on that side. We have to establish the ground on the load side, not on the transformer side. We'll show you that. So yeah, on a center tap transformer, if I wanted the secondary to be grounded, then I would have to ground it myself. Right? I understand that. So what happens? What you have to understand, this would be like a volt. If I was to come over here with a bunch of resistors, and I didn't need to do that. In fact, we got the circuit over here. Well, let me draw it back up. So if I was to come over here and put some resistors, and let's say this is a 10K and this is a 10K. And now I'm going to come over here and put this across the DC source. Right? You understand? So I come over here, and let's say this is 10 volts. So this guy's going to drop 5 volts. This guy's going to drop 5 volts. Right? You understand? Now, if I come over here and reference this to the center, right? You understand? Right? If I move it up here, this is going to be positive. If I move it down here, it's going to measure negative. Right? You understand? Everybody understand that? So what we're saying, maybe in a different way. So 5 volts, 5 volts. You okay? So if I measure from here to here, that's right. So that would be 5 volts here, 10 volts across here, right? So if I come over here and measure from here to here, it's going to show a minus 5 volts, right? You understand? Yes or no? Huh?
DC, I thought it both got positive 5 volts, right?
Well, it all depends on where your reference is at. Okay, understand what I'm saying? So, if I was to come over here and reference right here to the center, and I was to come up here and put my meter right there, right, you understand? It would measure a positive 5 volts. If I move it down here, it's going to measure a negative 5 volts. Understand? Because this is where the negative, this is where the common of my meter. So right now, this, if I reference right there, this is good. This, if I do my transformer, so if I come over here and look at this, if this side of the transformer is positive, this side of the transformer would be what? Negative. Right? You understand? Okay. But now let's move down to this one. This would be more negative than that one, right? You understand? Yes or no? But if I reference to this right here, it's going to be, so this is going to be positive in reference to that, right? You understand? And this is going to be negative, and this is going to be positive in reference to that. You understand that? So what happens if I come over here and throw this on my power supply? So I'm just going to draw the secondary. So what I'm going to do, I'm going to make a positive power supply. So I'm going to turn my anodes toward my AC source. So we couldn't do this directly off Alabama Power because this requires a center tap power supply. I mean a center tap transformer. And we're going to take the cathodes and connect them together. And then I'm going to come over here and go to the load. Now, let's say it's a positive alternation. This will be positive. This right here would be negative. Everybody okay? This would be positive in respect to that negative. This would be negative in respect to that positive. So I'm going to come over here. I'm going to put a plus right there. I'm going to put a minus right there. This guy is forward biased. This guy is reverse biased. This guy right here would turn off. This guy here would turn on. It would let the positive alternation come through to the load. But not the 12.6, the 6.3, right? You understand? Now, during the other alternation, everything swaps. So now this side of the transformer, the full transformer would be positive. This is going to be negative in respect to that. This is going to be positive. This is going to be negative in respect to that. So now this transformer here this diode here turns off. This guy right here turns what? On. So, but what's happening, so the first time, let's draw the current flow. So let's drop back to the first alternation. And let's get the current flow, because what we're going to see is the current flow through the resistor is the same direction both times. So we come over here, we start off, let's do it in a different color. So we started off with what? Plus, minus, plus, minus. Which one's on? Yeah, so the top one's on. This one's what? Off. Here comes my current, guys. It leaves this guy right here because this is negative. Comes back, comes up, does what? Goes back up through the resistor, comes back, and goes back to the positive right there. So that's what it's looking for. So the direction, so that makes this negative, that makes this positive. So I get a watt pulse out. I get that, right? Okay, is everybody okay? Now on our next alternation, this is negative, this comes positive, this is negative, this is positive. This guy right here turns what? Off. This guy what? Turns on. Here we're flowing from the negative, it comes out, comes up through here, goes that way. Now it comes down through here and goes back to that diode because it's looking for the positive that it was generating. So what I get here is I get this. My next alternation, I get this. My next alternation, I get that. My next alternation gets that. So this is why we call these guys full wave power supply. Now you're only getting 1/2 of the transformer. So even though it's a 12.6 volt transformer, we're only using one side of the transformer at a time, right? You understand? So when I calculate my voltage, I'm not going to use the 12.6. I'm going to use the what? I'm going to use the 6.3. So what would my output voltage would get out? Well, this right here gives me 2 V peak over pi. This guy over here gives me 2 V peak over pi. This guy right here gives me 2 V peak over pi. So now we're not averaging 0 into the mesh, right? You understand? So my DC voltage, volts DC full wave is what? 2 V peak over pi. Or this is where the 0.637 are. So guys, what should I expect to measure? I only got one diode. So I'm gonna pause this while y'all calculate it, and then we'll get. As the capacitor charges up to peak, where's my marker at? There it is. So what we do is we charge the capacitor up to peak, and then it discharges. And then what we do is we pick it up on the next peak. So if you was to actually look at the alternations, you'd see that ripple's doing this across the top of this thing. And we'll see why and what's going on that later on. But all we wanted to do is try to move toward, but it's still what we call unregulated, because notice when I put a bigger resistor across there, then it discharged faster, right? You understand? So the average voltage will vary. So we call that unregulated, but we're moving more toward DC, true DC, instead of this pulsating stuff. Are we okay? Okay, guys, we got one more to look at. This is what we call a full wave center tap. Full wave center tap. I thought I already said it before. So this is a full wave center tap rectifier. Now what's the advantage of it is we're going to get more DC out of it, right? You understand that? Okay. And of course, it's going to be easier to filter. It's going to take a smaller capacitor to filter. And we can actually calculate the filter size. We'll show you how to do that. So basically, after we get through with this, you could build your own power supply. And that's it. And when you're in electronics, that's a really good thing to have, especially a variable power supply, because you get some loads, you know. So you might have a car stereo, and you don't have to hook up a 12-volt battery to it. You can just do what? Power it up with your power supply that you build. When I went through here, we had a course called electronic fabrication, and that's what we did in the class. We built our own power supply, designed and built our own power supply, which was a really good class. Don't have to do that anymore. Center tap, full wave rectifiers. Everybody okay here? Any problems? Now, what I'd have to do here, if I wanted to change this to a negative power supply, what would I have to do? Well, I'd have to change both diodes. I just can't change one diode, right? You understand? Okay. So if you change both, if you only change one of them, you end up with a short circuit. Because when this guy here's forward biased, the other one's forward biased at the same time, right? You understand? So you have to swap both diodes. But all I'd have to do this, if I swap the leads on the transformer, what would it do? Nothing, right? As long as I left the center tap alone. But what I would do is I would come over here and swap the two diodes. So all I have to look at is I don't have to figure out current flow. I just look at the diodes. If the cathodes are pointing toward the source, then we have a negative power supply. So that would be all that would be required for a negative power supply. So when you look at it, all you need to do is do what? Look and see what's pointing toward the source. If the anodes are pointing toward the source, it would be a positive power supply. If the negatives are pointing to the source, it would be cathodes are pointing toward the source, it would be a negative power supply. The math is the same. The only thing that's going to change is what you put, whether you put a minus out there or don't put a minus out there, right? So let's look at one more. This is called a full wave bridge rectifier. And this is what we do. So we use 4 diodes. Now, the advantage of this guy is one, diodes are a lot cheaper than transformers. Center tap transformers are a lot more expensive than untapped transformers. So a full wave rectifier, a full wave bridge rectifier would be cheaper than a full wave center tap. But we're going to lose about 1.4 volts. What they're doing here is on this diagram. This is not in your textbook. This is an image that came out of a different book. Is normally if we wind a transformer, if we wind them in the same direction, then that means when the magnetic field is coming out of this one, it's cutting that one. So what happens on a transformer, if you wound them on top of each other, your secondary is going to be 180 degrees out of phase with your primary. And normally that makes no difference. And on power supplies, it makes no difference because you're going to hook your diodes up, right? You understand, and get either a positive power supply and a negative power supply. What they're trying to do is this wouldn't be true. These dots is saying, okay, these things are wound opposite of each other. If they're wound opposite of each other, then when the primary is positive on the top, the secondary will be positive on the top. And that's what the polarizing dots are being put in. Everybody okay? And it makes it a little easier to explain a full wave rectifier. So what happens is, notice up here, they got what at the top? Positive, and they got this at the what. Now, as soon as I come over here on my diode, and I take this positive over there, as soon as I see that positive on that cathode right there, I'm going to say this guy's what? Off. As soon as I see the positive on this anode, I'm going to say this guy's what? On. That makes sense? Yes or no? So positive on the cathode is going to turn it off. A positive on the anode is going to turn it on, right? You understand? Now let's look at the other side. Here's the negative. That would be a negative right there, a negative right there. Which one's set up to be forward bias? This guy would be on. This guy right here would be what? Off. Current comes up here. Comes out of the negative side, right? You understand. Does what? Goes through my common. Comes up, goes up through my resistor. Can't go this way. Why can't it go this way? This guy's off. It would flow back up this diode, and it's looking for its positive, right? It's not looking, it's looking for its positive, and it would flow right there. Now, of course, what we're going to lose is we're going to lose about 1.4 volts. Why are we going to lose 1.4 volts? Yeah, it went through how many diodes? 2. Okay. Now, on this other one, notice what they did. They changed polarity. So I'm going to put that negative right there. I'm going to put that negative right there. This guy is definitely going to be what? Off. This guy is going to be what? On. I'm going to bring this positive. I'm going to put that positive there and put that positive right there. This guy's going to be off. This guy right here is going to be what? On. So current leaves the negative side, which now the negative side is here. It's going to flow through here. It's going to go through this diode, go through our common, come over here. That's a piece of wire, right? Come up through here. Not going to go up because this guy's what? Off. It's going to come back through here. Now notice both ways the current came through that direction right there. Everybody okay? So that means this was always negative, this was always positive. I'm going to get this out of it. I don't have to use a center tap transformer. If I use a center tap transformer, I can get both negative and positive supplies off a single transformer. You see that done all the time. I'll show you how we can do that. Now I like to draw it like this. This is why it's got this name. We came up with this, and they came up with resistors like this, and they refer to this as a Wheatstone bridge. Now, I like to draw it like this because it's a lot simpler, and it makes it, to me, it makes it easier to understand. I just like to come over here and take 2 wires like this. See that? And I'll come over here and I'll do this. And then I'll bring my AC and put it right there. And this will be my DC up here. And this is the same circuit. See that? Yeah, AC's right here. This is my DC load. Same circuit. So my AC is supposed to see an anode and a cathode. See, so here it sees a what? An anode, a cathode, anode, a cathode. On one side we have common cathodes, on the other side we have common anodes. Now what's nice about this thing is I can take this thing and flip it around, and I've got a negative power supply. I can take this and flip it around the other way. I got a positive power supply. Guys, this guy, and so what we'll do is I'll show y'all some of these next class, is they integrate these things. So we'll have a device that looks like this, and I'll show y'all some. It's got 4 leads coming out of the bottom of it. 2 of them are labeled AC, one of them's minus, one of them's labeled plus, and one of them's labeled minus. All I do is establish which is my common. If I want a negative power supply, I make my positive common. If I want a positive power supply, I make my negative common. and these are called bridge rectifiers. You can buy them any size. I'll bring you some big ones over here that's rated like 50 amps. I'll bring you some that's rated at milliamps. And they're integrated. Now, what's nice about having them broke up individual like this is if this diode goes bad, you can replace that diode. These guys are cheaper to buy, but if one of your diodes go bad, you have to do what? You replace the whole thing. So integrated bridge rectifiers are cheaper to install, but they're more expensive to replace, right, if something goes wrong. Separate diodes, they cost more expensive to install because they're not integrated. You're buying them entry, but they're cheaper to fix. And you see both ways. A lot of your engineers like these things. You'll see these used all over the place. But then again, you might see them use individual diodes. I can't remember what the trainer uses. I think the trainer uses the bridge rectifiers, the bridge that's inside a single unit.
The bridge one time you talk about?
No, our trainers.
Oh.
Yeah, what we're going to do, the ones that get stuff in it all the time. We'll take one of these apart, and we'll pick out, once we get through the whole thing, we're going to take this apart, we're going to find the bridge rectifiers, right? We're going to come up here and do what? We're going to find the filters, we're going to find the regulators. We'll look at the different types of regulators. This has some fixed regulators in it. So, when we look at this thing, and we're not going to do the math on this right now. We'll do that next class. So the power supplies we have available on this trainer is we have these guys right here. These use fixed regulators. So we have a minus 12, a plus 12, a plus 5, right? And then we have these guys up here. This is variable regulators right here. And that's where we use these knobs right here. So we'll look at both of those type of regulators. These use integrated circuits, by the way, instead of using discrete components. This is a 12, this is kind of misleading. This is the 12.6 volt center tap transformer. But they're showing 0 in the center. But that's not exactly true. It's actually 12.6. So if I went from here to here, we have a 12.6. If I went from here to here, I have a 6.3. So that's the transformer right there. It's almost identical. Well, not. It's actually this transformer right here.
So that's what you got current.
Yeah, this guy. And what it is, it's got multiple windings, and we'll look at this guy. So this gives us this. We use this one transformer for all these voltages. So I wouldn't want to use a big transformer to get 6.3 volts because now I'm gonna have to have resistors, or well, we'd dissipate a lot of energy, right? You understand? So this has different windings on it. Some of them center tap, some of them are not, some of them are untapped, and so this is a multi-winding transformer. We have 2 wires for our primary, and then we have all these different wires for our secondary. And I'll show y'all. We'll actually look at the schematic on the trainer and figure out how this transformer works.
I'm gonna ask you a question. I don't know if it's gonna make sense. So from the same transformer, I could use the 12.6 twice.
Sure. All we have to do is we just isolate. We isolate the transformer. So we come over here and we have a. Let me find some. I got a lot of space. Well, so we got a primary. Right, you understand. And then we got this big old metal thing running through there. Well, what's to prevent me from putting one guy right there, and then I put another guy right here, I center tap this one, I come down here and put him up right there, so we can use this. Now, the primary is going to have to support the current of all those secondaries, but we can put multiple, and what's nice is this right here might be 6.3, or it might be something else. This might be 12.6. It don't make any difference. That's what we call a multi-winding transformer. So you'll see this are used a lot in electronics because instead of me putting one transformer to do this and one transformer to do that and eat up all this space, then I can do what? I can use one transformer that services all the DC voltage needs that I need in my system. So this is a multi-winding secondary. We can have multi-winding primaries, but those are for we use to set them to run on different primary voltages. When y'all take motor controls, you'll see that. So we got a multi-primary transformer up there. So we got two primaries, and then we can change the turn ratio. So they usually cross them like this. So if I come over here and jump that, then we get this many turns, right? You understand that. If I was to come over here and come over here and put the jumpers right here, from there to there, and from right there to there, then we got them in parallel because they're conducting more current. But now I get half the windings in my primary. Well, over there, we can, all our devices is set to run on 120 volts, but I can run it off a 440 or 240 supply. We can either wire it to divide by 4, or we can wire it to divide by 2. Does that make sense? So we have multi-winding primaries. These are usually transformers that can be wired to run different primary voltages. And then we have multi-winding secondaries. This is where we can get multiple voltages off one primary, right? You understand that? So transformers can get very expensive. But the problem is this guy right here might have 4 different voltages. This guy would be cheaper than me having what? 4 transformers. And then not only do I have to have 4 transformers, I got to have the space for what? 4 transformers. So you'll see this done a lot, especially like on the trainer. It's got all those different voltages, right? Plus 12, minus 12, plus 5, minus 12, and then we got the plus 5 volt supply, and then we've got the variable supplies. So instead of coming in and putting different transformers, they just have one transformer. Are you okay? That makes sense? So this is what we call a multi-winding transformer. And that's why we got all these wires coming out of the secondary, but we only got one primary, right? So you can run into both of those. So we'll figure it out. We'll come in and we'll look at the schematics on the whole power supplies inside the trainer. Predominantly, that's what that trainer is. It's a bunch of power supplies, right? Makes sense? So that 6.3, it's a dedicated transformer, so it's not running anybody. So that 6.3 that comes up, that 12.6 that comes up to the side, it's got its own dedicated secondary. So it shouldn't affect the 5 volt supply. It should have nothing to do with the plus 12, minus 12. We'll look at it. It's pretty neat. And I'll show y'all some bridge rectifiers, some full-blown bridge rectifiers. We'll wire it up with actual diodes, because that's what you're going to have to do. And we have problems with that too, where people want to hook them in parallel and that kind of stuff. None of those diodes are in parallel, right? You understand? Just because you have one lead connected to another lead, to be in parallel, both sides of the component have to do what? They have to connect, right? Okay. And then we'll calculate that out. And y'all are on the way. Then we'll figure out later on how to calculate a capacitor to run our current. And then we'll see what we can do about regulating. Any questions?
So
Power supply.
you got a quiz or quizzes for this chapter?
Not this chapter. You should have, and thank you for bringing that up. Ooh. So what have we done? What lectures have we done so far? Did basic AC, right? Oops, dang, I keep using the wrong password. It takes so dang long to say you screwed up.